Okay, so welcome to another video of transportation methods, where in this video we'll be exploring the idea of a co-current heat exchanger. Okay, so pretty big idea in chemical engineering. And the question at hand is, how should we derive a term, an equation for the Q term, Q being the heat transfer rate. Okay, remember everything is in rate. Typically you see Q as in heat, joules, but since all of our terms are in rate, this joules becomes watts, so Q is heat transfer rate. Okay, so we start with some expressions from the textbook describing dQ, differential heat transfer rate. Okay, and we have these over here. Now notice we have this delta T. And what exactly is delta T? Well, delta T would be the change in temperature. Okay? See on the diagram here, the change in temperature between the two flows. So we can go off and describe delta T by using a differential. We can say that the differential change in temperature is equal to the differential hot temperature minus the differential cold temperature. Okay, then this is where these come in. Okay, a good visualization from the textbook. So, and you notice we have this here. We have dQ. All right, we have dQ given in terms of heat capacity and differential hot temperature, and heat capacity differential cold temperature. See, it's a little scrunched up at the end, but it's there. So we can go off and throw that in. D delta T is equal to, well, actually first we need to relay some algebra. This differential hot temperature becomes dQ negative hot and d differential cold temperature is equal to differential heat transfer over positive heat capacity. Okay, so now we're left with dQ 1 over CH plus 1 over heat capacity. So I took care of the negative there. Okay, and since this negative I need to pull out and put instead of the dQ. Now we have this dQ term. Well, we can just use that to plug it in. Okay, and now it might seem odd at first because hey, we're finding a term for delta T, but then we're plugging the whole expression back into it. What's going on? Trust me, it just works out. The algebra will work out. It's a little tricky algebra, but it will work out. So this will become the differential change in temperature is equal to overall heat transfer coefficient delta T in differential area over 1. Okay. Now what? Well, I can bring this to the other side. Okay. This delta T term to match it up with the differential change in temperature. So differential change in temperature over change in temperature is equal to U delta T. Don't forget the negative. I think I dropped the negative there. U delta T 1 over CC, not CH, plus 1 over heat capacity of the cold stream and differential area. So now what? Well, this looks like a differential equation that we can just integrate, right? And the bounds of integration will be 1, 2, 2, 1 to 2. And 1 and 2 being these positions of the heat exchanger described there, in and out, essentially. Okay, so this becomes natural log of delta delta T hot over delta T cold, I believe, is equal to the negative heat transfer coefficient multiplied by the change in temperature multiplied by area of heat transfer, okay? Let's finish this parenthesis. No, actually this should not be hot and cold, but rather position 2 and 1, okay? And this delta T2 and delta T1 is described there in the graph, okay? Remember, this is the hot stream in the co-current heat exchanger, and this is the cold stream in the co-current heat exchanger. So now what? Now we have these heat capacities to take care of, and we can take care of them using a pretty nifty expression. Now you know that from general chemistry you have Q equals mc delta T, right? Now how about if you had flow rate? Well, if you had flow rate, then Q would equal mass flow rate, this C constant pressure of the hot stream, and then the T hot in minus T hot out. Okay, and this is where our we're gonna find our delta T1 and delta T2. Okay, and the same goes for the cold stream. Q is equal to mass flow rate. Really, this should be hot heat capacity at constant pressure of the cold stream, and the cold temperature in minus the cold temperature out. Okie dokie. And these terms here both become abbreviated as CC and CH, which, hey, we have right there. So let's go ahead and throw that in. This natural log delta T2 over delta T1 is equal to negative U delta TA of Q. Over. Did I flip something here? I did. These are in the denominator, so I should take the reciprocal. So this should be T C. No. Temperature hot in minus their temperature hot out over heat flow rate plus temperature cold in minus temperature cold out over heat flow rate. There we go. And what we can do is, well, we can pull that Q term out, and that's what we're solving for, right? We're solving for an expression for heat flow rate in terms of overall heat coefficient, the area of heat transfer, and the temperature difference, right? So we have negative U delta T area Q, and we're left with T hot I minus T hot out plus TCI minus T cold out. Okay, now what? Well, we bring this over. Well, before we do that, this right here, if we bring this can be rearranged in convenient terms. Okay, we can say that this is equal to the temperature of the cold stream out minus the temperature of the cold stream in minus the temperature of the hot stream out minus temperature of the hot stream in. Okay, and this can end up be describing as delta T2 minus delta T1. Okay, rather convenient, right? And then we bring the Q to the other side and put the log in the denominator. So now we have Q equals negative U delta T multiplied by the area multiplied by the difference in temperature at position 2, difference in temperature at position 1, over the natural log of delta T2 over delta T1. Okay? And there you have it. Here's our derived expression for a heat transfer rate as a expression of U, overall heat transfer coefficient, delta T, change in temperature, and area of heat transfer. Okay? Now this right here is the idea of log mean temperature difference, and it might not look like a mean, but I assure you it is. You have your arithmetic mean, your geometric mean, like let's see, arithmetic mean is like a plus b over 2. Geometric mean is a times b radical, and then you have your log mean difference. Okay, and this log mean difference is important, and as is our terms for delta t, because if you go off and take a look at the textbook, you see that, well, delta T1 and delta T2 for a counter current, it's the same. So hot 1, cold 1 minus hot in, cold out, right? These terms delta T1 and delta T2 remain the same for a co-current and counter current heat exchanger, such that this expression becomes valid for both situations of co-current and counter current. And that's why this is so useful and ubiquitous if you ever go off and design heat exchangers. Okay, so with that, this concludes the final part of homework 5, and this is the last video for this semester. Okay.